Welcome to our next lecture on condensed matter theory. In this video I want to talk about the Drude model and give some historical context on why Drude came to his model and the importance of being able to describe metals or materials, and for Drude metals. The research on metals and understanding metals has historically an enormous importance because of the economical value that metals have. Starting from the prehistoric dates where, well, if you were able to make your sword or your spear points out of metals that were stronger than the armor of your opponent, that of course was a clear advantage. So there has been a huge historical fascination with different metals. And things like gold you can find without having to do much effort in riverbeds. But well, gold, because it's so soft, is not so good for making tools. And the same is true for copper. People in the ancient time also found metals in meteorites that definitely has been used to make tools from. Although the historical context is actually not as clear as I thought it would be when I tried to look into things, then it seems there are still several controversies about where and how old actually these metal tools are. But what is known is that, well, at some point humanity started to make bronze by mixing both copper and tin. And the nice thing of bronze is that it's much harder and therefore you can use it to actually make tools from them. And we can also understand the order in which people started to use metals. Copper you can find, and if you mix copper with tin, then you can make bronze, and tin melts at 230 Celsius, so that's of course easy to work with. Copper melts at 1080 degrees Celsius. So you can also melt copper in a campfire, which is roughly 1100 degrees Celsius. Iron is much harder to make. Iron melts only at 1500 degrees Celsius. So for that you really have to build furnaces. Well, the research into that of course led to a study of metals and their properties and how you can turn one metal, copper, or a mixture of copper and tin, into another metal that is much harder. Well, that progress has been slow but steady, such that people were able to improve the stress and the stiffness and the durability. Think of stainless steel, where you mix in some carbon into your iron, or you change the ratio of carbon in the iron to change how much it rusts, what the stiffness is and what the strengths are. So experimentally people got things pretty good under control. But the theoretical understanding was actually not so good. And one example I always find really nice to look at is Newton. We know Newton, of course, for his work on optics and his work on gravity. We do not know his work on metallurgy or alchemy, as people would have also called it back then. And there's a very good reason for it, because well, what he wrote down is just not so good. It doesn't work, it's not correct. And it's very understandable that people had such a hard time to understand material properties. Because in order to understand the material properties, you have to have knowledge on the electron, because that's basically what determines your material properties. Even things like strength and stiffnesses is determined by the electronic structure. And the electron was only discovered in 1897 by Thomson. And then of course you have to understand the laws of the forces on these electrons, and that is in a large part quantum mechanics. And quantum mechanics, well, only came really alive with the equations of Schrödinger in 1926. Actually, there is a beautiful paper of Dirac from the same year. It is on Moodle, and you also find a reference in the script, where he basically describes the equations of Schrödinger in compared to the quantum mechanics that was developed before by Heisenberg in the many electron case. And these are two very short abstracts or paragraphs that very much show you the importance of Schrödinger's equation for quantum mechanics. Now we will discuss the Drude model this week, and the Drude model was developed in 1900, and that is of course before the dawn of quantum mechanics, but it is after the discovery of the electron. So what Drude did is using Maxwell's equations to describe the forces on electrons. And with that, there are several things that you can explain. There are of course a lot of things you cannot explain. But this is only developed in 1900, and only in 1926 then people really start to be able to describe the properties of metals and materials. And you see that then also the progress really started in what we can understand and what we can do, leading, for example, to the electronics and the integrated circuits in the semiconductor industry that we have nowadays. I find it always amazing to realize that the Eiffel Tower, that was built in 1878 to 1898, was developed before people realized that you have electrons. So before people actually basically knew any fundamental properties of the metals and were able to understand where these things came from. So you could turn iron into steel with very different strength and stiffness properties, but why that was and how that actually functioned, well, people had experimental control but no understanding. And even when you look at electronic properties, which are the basic ingredients to understand strength and stiffnesses, when Ohm, for example, introduced his law in 1827, where he said, well, the current is proportional to the voltage that you put over a wire divided by the resistance of that wire, and that resistance is a material specific constant times length divided by area. His findings were met with extreme skepticism. And well, a lot of experimental experience came from sparks conducting through gases. You take two charged balls and you look at discharge via the air. And a gas is an insulator, so there is no current flowing until the electric fields are so big that you can break up your molecules. At that point you generate ions and you get ion conductivity. So the conductance of a gas really doesn't follow Ohm's law. And at the same time, it's quite logic that people in that time would be skeptical about people doing science of metals. Well, that's basically metallurgy or alchemy at that time, and it was not really known as a quantitative science. So it took Ohm quite some time to get accepted. And one of the successes of Drude's model in 1900 is that he can explain Ohm's law, where it comes from, related to material properties, understand why in some materials it should be bigger than other. And he also was able to explain several thermoelectrical effects in his paper. Now we will in this lecture of the Drude model not follow the historical context. Drude's papers are historically nice, but I wouldn't recommend you to read them at the moment. He argues a lot, does an electron have a mass or not, and how do you work with the ether? And those are not questions that we have to ask ourselves. But we'll look at a few properties of metals that we want to explain within Drude's model. And we'll start by deriving Ohm's law, so relating the current through a metal through the voltage that you put over it. Then we look at the Hall effect, which was discovered in 1879, where you have not only a current but also a magnetic field and therefore a Lorentz force, which then builds up a voltage perpendicular to the current and perpendicular to your magnetic field. And we'll explain this, and we'll also show what you actually measure with the Hall effect, and show that with this you can really determine the density of charge carriers in your system. So it's an experiment that is still widely used in semiconductor physics to discover the number of free charge carriers that you actually dope. Then we'll have a look at the reflectivity of metals. and explain why metals are reflective. And in 1933, people discovered that the simple alkali metals or aluminum become transparent in the ultraviolet. And that's of course strange, because we're always used that metals absorb light. So you use them to make a Faraday cage to screen electromagnetic fields. But it turns out that at some frequency high enough, all of a sudden the metal is beautiful transparent. And if you would do the same with a glass window, actually it would absorb. So completely opposite than what we're used to in the optical visible wavelengths. And actually this you can beautifully explain with Drude's model. All the theory was there when they observed this. So that's quite a success of Drude's model. And then the last property I want to discuss. There are many more that we could have focused on, but I think, well, if I discuss these 4, you should be able to derive these others whenever you encounter them. And the last method I want to discuss is the specific heat. And the specific heat is a case where the Drude model and classical physics does not describe the observations at all. And actually there is a very deep reason why this is the case that goes back to really quantum mechanics and the statistics of fermions that is behind there. So we'll end this week with a question for you, and there you have to try to figure out why the specific heat of a metal goes to 0, or well, it does goes to 0 at 0 temperature in the experiment, and it doesn't in the Drude model, and it doesn't in basically any classical model that you can think of. So we'll discuss why this is weird, and then next week we'll come up with a solution. When we go to the Sommerfeld model, and the Sommerfeld model is basically Drude's model, where we replace the classical motion of electrons by a quantum mechanical motion and the Fermi-Dirac statistics of the electrons. Well, then let's go. In the next video I will introduce Drude's model, and then we'll have 4 videos where we discuss the properties, or 5, because I split the reflectivity and transmission and plasmons into 2 videos on the different properties of metals. Stay healthy. We see each other in the next video.